Yeah. I think everything's good. All right, let's do it. So it's the final session. And I can't believe so many people made it all the way to the end. Thank you for being here. It's a pleasure. And I hope it's been useful so far. I hope this part's going to tie it all together nicely. And by the end of this, yeah, like I said before, you'll be in a really top bracket of people who understand this stuff. It's very, very recent. This is the most cutting edge stuff that's happening right now. It's the most cutting edge stuff I've ever taught. There's a lot of it which is still a mystery. And maybe we can fill in a little bit of those gaps today and explore what might make the system work a little better with the setup that we've got so far. But today, I'm going to go through reinforcement learning for human feedback. It's a step 3 that you've seen in this diagram down here below, which covers the steps of how ChatGPT like models, including ChatGPT, InstructGPT, and others are trained. And this thing should really tie together the reason why we've done step 1 and step 2. So we will pull in our supervised, trained, fine-tuned model. We will train the reward model with some more data, and I'll show you how to do that on GPU. And then we'll combine all of that into this reinforcement learning setup, which happens on the right-hand side, which is aims to take what the reward model has learned about what's good and make the model align to those kind of behaviors, like behave safely, behave professionally, behave ethically, and such. So that's what I want to go through. After this, we are, what are we doing, Ahmad?
We're going out to grab drinks, and I want everybody there at 9:30 p.m.
Okay, cool. So we're going straight from here somewhere, and then we're going out after as well, right? Okay,
and
cool.
We might end up in a club as well, so if you want to see Harry,
yeah, it might get crazy. So be there and don't miss that. See me in my element, of course. So that's what we're doing after. I'm going to go through this implementation, a bit of theory, a bit of code, and then we'll do a quiz. Again, this is the final day, and as you know, there's a giveaway. So I got a t-shirt, I got a hoodie, and I got £100 in cash, which I'm going to spread between 3 people. If you want to be in a chance of that, then just let you know. Post a picture, say something epic about us on LinkedIn, tag me, tag AiCore, and then I'll look through the best ones at the end. And the final thing is the quiz. So we're going to do a quiz at the end. It should recap a lot of the knowledge that we've covered, and there will be one of you crowned a champion. So any questions previously, people want to catch up on stuff about step 1, step 2, or step 3 that they want to raise right now? Cool. All right. So Josh, what was the point of step 1? Step 1 was collect demonstration data and train a supervised policy. Why did we do that? Phone a friend, you need Nick, James, sorry. What was step 1 about? Just give us a rough idea. I can fill in the gaps.
So, like, we train data set, we're going to need responses.
So we've got prompts and responses in a data set. What do we start from scratch? We got our own model. We take a pre-trained model from Hugging Face, and which model did we start with? GPT-2, yeah. And which model, Lily, did OpenAI start with? Sorry? We used GPT-2, yeah. And what did OpenAI start with, which we don't have access to? A bigger model? Yeah, 3.5, that's right. So the starting point of step 2 was to take 3.5 off the shelf and collect a bunch of labeled data, that is prompt, pairs, and pass those through this GPT model to train it in the same way that it's trained, just on a data set stuff which looks a lot like, well, which is chatbot response conversational data. And the point there is that you get a you get a language model which knows not just how to predict the distribution over the next words for any arbitrary kind of text like stuff you might find on the internet and Reddit and books, but it knows how to predict words and generate sequences as a result in the format and style of, how ChatGPT does it. But there's still a bunch of problems with that. You can get a lot of things like just very short responses or inappropriate responses, or just in general misaligned with ethically bias-wise responses. So steps 2 and 3 are what we use to try and, as I keep saying, align the model with human intentions. So we want to get to a point where we can do this step 3, which is basically you've got an existing model, it can make predictions about the prompts, about which responses should come back, and you want to be able to give the model feedback. Is it doing well? Is it not? Based on that. And whether it's doing well or not will depend on what the reward model tells it to. So the reward model is about taking a prompt response pair and producing a score. And once you've got that score, then you can say, okay, look at the gradient of that score and update the model parameters to improve that. And that's what this step 3 over here is about. Okay, cool. So, Constantine?
So what are the advantages of this compared to just having like one big kind of net? Now we split it into kind of two parts.
Mm-hmm. Yeah.
Why is this so much better than just having one big net?
Yeah, so you said we split it into 2 parts. You've got the language model and the reward model. Why is that better? So at the end of the day, we're just going to take the language model. That's the part that we really care about. The reward model is really something that we come up with so that we can do this process, which kind of pushes the language model further and further to align with those values. So this reward model is basically a model of what humans think is better. That's what we've done in step 2. We've gotten a load of different responses for the same thing. And we've told the model, I want you to basically tell me which of these are better. So hopefully that reward model encodes what better means.
Is all of the information our reward model is like human generated?
Sorry?
Is all of the information you have in the reward model like human?
Yeah, the reward model is trained on all the data collected at the beginning, and then this reward model is trained on a single prompt, multiple responses, which ones are best. So it's a data set of ranked responses. Yeah. Does that answer the question? Is there more to that? Do you want to go deeper?
Yeah. I don't know.
Okay, cool. All right, let me know if there is. Peyton?
I have a question. So why do we do the fine tuning of the game? Couldn't we just kind of use the reward model with the base chat, GPT-2? What's the benefit from fine tuning? Then wouldn't it
Yeah, that is a good question. That's a good question. One thing is that we know supervised fine tuning really works. Like it's very quick. There's a lot of data sets already available for it that make it work in a lot of other domains, like question answering or text summarization. And so it's like tried and proven practice. It can show that you can take general appreciated models and have them focus on a special domain. So I guess there probably is. I'm not sure what would happen if you just did the reinforcement learning stuff. That would be interesting. Maybe we could try it today if we can see if we can get anything out of that. But certainly fine tuning is like a quick, easy, known to work process that will help it to converge to model the kind of thing that you want. Whether it be questions, whether it be summarizations, whether it be just like language like a chatbot in a particular style. Yeah, because GPT-2 is trained on so much different random stuff that it probably is not going to. Well, as you can see, as we saw the prompts the other day, it doesn't behave like the way you want. You want to add more to that?
No, I think that's
Okay, cool. All right. David, do you have a question?
I just wanted to check my understanding. So the reward model purely for further training of the model, and it's not going to ship the final version of the model.
Yeah, that's right. Yeah. So the reward model, as I said, the point of it is to encode like things that you want, things that encode the thinking behind humans saying this is better, this is worse. And once you have that, then you can use it to give feedback to the model iteratively.
Like bigger scales.
Yeah, and without requiring labels as well in this third step, which is an interesting point, right? So as long as the reward model got good enough to start with, it can generate its own responses now. And then we can use those without having a label to compare them to, like we needed in step one. In step one, we needed a label to compare to. What words should it predicted at that point? Yeah, does that make sense?
Yeah.
Cool, great stuff. There's more hands, but they've gone down. Good. Cool.
So for pre-training GPT-2 for the reward model, were humans used for prompts as well?
Yeah. So in the step one, this collecting the demonstration data, we've collected a range of data sets basically. One of them is the supervised fine-tuning data set, which is both prompts and responses. In the second step, we've got a data set just of prompts and ranked responses. And in the third stage, we've just got a data set of prompts, which we're going to produce responses to and see how they get fed back. And all of those things, the prompt and responses and the rankings, which make up those three data sets, they are labeled by humans, by 40 people. There was another number there as well, but it was 40 people and about like 30,000 examples overall. Sorry, that's in the Instruct GPT paper. I don't know how much it is for the ChatGPT paper. Yeah, David, good, cool. All right, cool. So that's basically the overall setup. We've seen how to build this model. I'm going to pull them in below, do a few little extra things, and some practical tips to show you there, and then we'll look at how that would go into this algorithm. Disclaimer: there is a worrying mistake which I will get to, and I don't quite know the solution. So if we don't get it fully implemented, at least it will be a good overview, like what this thing roughly looks like in the code. But there is one missing piece, which I'll point out, and we'll figure that out as soon as possible and update this with it. Cool. Any questions on top of that? Okay, cool. So what is reinforcement learning, firstly? Can anybody describe it to me before we get into that? How would you describe what reinforcement learning is? Anybody remember the Pavlov dog story? There's that story, right, of some scientist, someone Pavlov, and he had was that Hanover? No. And he had some dogs, and he would ring a bell every time he fed them, and when he fed them, they salivated, and then over time that conditioned them to whenever he rang the bell, they would then salivate regardless of there being food. So it was conditioning, basically. When I ring the bell, do the thing I want you to do, which is salivate in that case. They learned that behavior from getting that reward, which was the food. And that's kind of the simplest introduction to reinforcement learning, is basically do things I want you to do, get a positive reward, and then hopefully that allows you to learn that behavior naturally. So the typical diagram that you see is something like this. This is the reinforcement learning loop, which is one of the big interesting areas of machine learning, which basically shows you how you can have some agent, whether it be a robot or a chatbot or whatever, interact with some environment. In our case, that's like a human in a chat, by performing actions, in our case, these responses to prompts, to produce new state, new chat. And as long as you can give it a reward, then you can tell it to update its policy. So the policy is something that just defines what do I do in a certain situation. We use a symbol pi for it, and we write A equals pi s. That means the action that I take is a function of my state, and function is what I call my policy. Policy takes an action, sorry, it takes a state, gives you a new action. And starting from the initial state, our chatbot is in, it's like empty chat or like start sequence token or something like that. It's gonna use that initial state S to come up with an action A, and it will produce, it will do this action to change the environment, or maybe the initial state is our first prompt, for example. It takes an action which is produce a response, and that changes the environment. Now, in this new environment really consists of the state pointing out, okay, what does the chat look like now, and the reward, which we need somehow. In our case, that's the reward model. So that's the reinforcement learning setup that we're going to look at. But to give another example, which might be more familiar, is like the DeepMind AI is playing Atari, right? Maybe that's a more familiar setting. And this might be easy to explain in that sense. So you've got this agent, which is like, you know, some character in the 2D Atari game. It's in some state. The state is all of the pixels on the screen at that point. It takes those into its policy. The policy defines what action do I take. Maybe that's move right and jump or something like that. It does that thing, and that produces a new environment, which is just like new, well, that goes into the environment and produces a new state. The new state is like, okay, the pixels have changed because the character's moved. And the reward may be like they get points or something like that in that situation. So that's the reinforcement learning setup. Can anybody give me any other examples? You can formulate like many problems like this. So I want to hear a few examples just so we get the idea clear. Alex, what do you reckon?
AI learns how to drive. Let's say you
Good
put
one.
it in like an environment on a racetrack.
Yeah.
There's obstacles everywhere.
Real world, yeah, straight in, cool. And so the environment's like a racetrack. What's the state in that case?
Position, velocity of the car. So at that position and the velocity of the car, decide where to go. You need to get to the finish line.
Yeah. And then there could be other things in there as well, like acceleration, or current wheel position, all that kind of thing. Yeah, exactly. And then what's the policy? What does that represent?
To get it closer to. Yeah, I don't really understand what
So just in general, the policy, right, is this equation. So if your state is the vehicle position and acceleration, the policy is going to take that thing and basically tell you what to do next. So, you know, you hear about policy when, you know, government policy or something like that, right? What does that mean? The government policy is just like, that's what they're going to do in that situation. That's what the policy outlines. And so that's the way I think about it. That's where the name comes from for me at least. Alex?
Joking back to network seems to be
So do GANs use a user reinforcement learning setup? That's not quite the same thing because you don't have this reward, and you don't really have this environment either. So it's more like you're producing a score and just back propagating it, but through two different networks there. Yeah. So it's not quite the same reinforcement learning setup for a Jones or Axera network. Yeah. Which one?
Could human evolution be considered reinforcement?
For sure. Yeah, definitely. You are an agent in this environment which has a certain state, and you know you can take actions and you can get rewards, or the opposite. So yeah, absolutely. Yeah, and that's why it's a really interesting framework, right? It's a really general framework that can be applied to all kinds of problems. So you know your mind should be teeming with ideas of how this is set up, and there's like really promising interest in this being the future of AI. And here we are for ChatGPT. This is behind the scenes, so it's a good application of it. Charlie?
How do you, once you've got your reward or punishment, how do you then update the parameters?
Yeah, so there's a bunch of different algorithms for updating the parameters. Like the simplest one would just be like, well, if you have a model that is something that tells you what reward you're going to get for every state, then you can basically, and you can differentiate that thing, then you can say just follow the gradient reward downhill. In different situations, you may not have that kind of thing. There are many different algorithms behind it, so we could break down them maybe later. Cool, that's a good question. All right. So in our case, it looks like this, right? So just to reiterate graphically what I just spent 5 minutes talking about, that's what we've got. Fine-tuned model. That's going to start off as our supervised, the output of our SFT process, the fine-tuned model there. The policy here is going to be something that takes the prompt, predicts the response. That is, as I keep saying, the prompt is how the model behaves in a particular situation. The situation is the state, and in that case, that's like the state of the chat. So when it produces a response, the chat updates, and the environment has a new thing, which is, well, it'll have a new, sorry, I didn't have the state over there, but the state would be like the whole chat so far. And in our case, this is where we've got the reward model. Because if we didn't have a reward model, we wouldn't have any way to know, like, is this good, is this bad behavior, and we wouldn't have any way to encourage it in the right direction. So we have put in the hard effort of collecting that data, that ranking data, so that we can build that reward model. If we didn't have a reward model, it would be hard to tell the model, you know, what's the right direction to go. and that kind of thing. And so in many cases in reinforcement learning, you don't have this model of the world. And so it can be different and tough. But in our case, we do have the reward model. Okay, so overall, like, this is a simple setup of how things could work, to the point that Charlie just made. So in our case, we've got these two different models. We've got this fine-tuned model on the left, the green one. That one's the one that takes a prompt and it outputs it. And this one, I've said, it's got parameters 5. So I should differentiate the parameters of one network and the parameters of another. In our setup, prompt comes in, response comes out, and then both of those things, actually, I should have put both there, they go into the reward model. The reward model is just another neural network. It's actually a transformer, not a fully connected network like we're talking about. And it outputs a scalar value, which is the reward. And that reward gets put into this function that we'll look at in a second, which is like some objective. That is the objective of the agent, the thing that it wants to achieve, the thing that it lives for, and it's closely related to the reward, basically. That thing is going to be a function of the parameters of those models, because that's where the reward came from, which goes into the objective. So, you know, in the video game setup, like, the objective may just be, like, you know, maximize the reward over time, paying more attention to nearby rewards, that kind of thing. In the case of the car, it might be like, don't crash, or you reach a maximum speed and don't crash, or something like that. So this reward, you know, many different problems, you have many different rewards, and that's the topic of reward engineering. How do you get the model to, how do you get the agent to perform the way you want? Can you do that by changing the reward, changing what it values? And there's really interesting stuff there. You can see you can get really complex behaviors from video games, or like you know, stickmen in game engines, those kind of things. You can get to do backflips and stuff just by changing the objective. So then what we'll do once we've got that is take the gradient of the objective. Okay, how do I maximize, in this case, the objective? And calculate the gradient as usual. That's with respect to the parameters of the fine-tuned model, which we want to update, and then update those parameters. Only those parameters. The reward model stays fixed. The reward model, we're hoping that already encapsulates all of the alignment that we want to perform, and so we just want to update these fine-tuned models. Josh?
So how does this take into
previous response and previous responses from the from like the same chat, or yeah, from the same chat. So they would actually, so I haven't been very clear here where I said prompt, but what I mean there is like the chat so far, so everything so far, ideally. And that's why, you know, transformers are nice for this, because regardless of the sequence, they can ingest it, and regardless of the sequence, as long as you can parallelize it, they'll produce predictions in the same time, regardless of how long it is. Yeah, that answers the question. Cool, great. So yeah, that kind of relates to the diagram above, doesn't it? Where in our case, we're getting out the new state, but it's not just a new prompt. That should actually be like new prompt and everything before. So you've got a long sequence of tokens. You want to predict what comes next. Yes?
So you don't change the parameters of your reward model.
Mm-hmm. Yeah.
Is that, and I assume that's very important.
Sorry?
I assume that's very important.
Yeah, exactly. Yeah, you have to freeze the, or at least in this setup, I don't know if there's probably some other exploration, and who knows what will come next, but in this setup, the reward model stays fixed. So we spent a lot of time and effort collecting the data set of prompts, responses, and rankings to train the reward model. Hopefully, all of that hard effort has allowed us to build a data set which captures those important things. And if the reward model is able to optimize down to conversions, then we want to keep that fixed so that we can use that as basically a critic for the model. Are you doing well? Are you doing poorly? And the value which comes out at the end, the reward, should reflect that. So we want to keep this thing fixed. At the end of the day, like I said, we don't really care about this. It's not that much use telling people, hey, this one got 100 points, that one got 104 points. It doesn't really matter that much. The point of it is to use it in this reinforcement learning setup to provide the reward, to essentially model the world where it will get, good upvotes, downvotes for good and bad behaviors from humans, and use those to update the fine-tuned model so that it can better generate text. because this one is the generator. This one is the text generator that produces responses. That's what comes out of ChatGPT when you hit enter. Reward model just scores it. Great questions, nice. Okay, cool. Yeah, so take a read through that stuff if you want. Now I've got this new data set, which is very simple. I don't even think we need to really implement that. But what this one is, it's a prompt data set. It's only prompts this time. It's only prompts. Previously we had for the supervised fine tuning, we had prompt response pairs. For the reward model, we had prompt response inputs and rankings as outputs. In this case, we've only got prompts. So I'm going to pick on a few people to help talk me through what's happening in here. Eunice, what's happening in the initializer? Question? You can't access which, sorry? Sorry, I should have mentioned this. The Colab notebook is in Discord today. I haven't put it on the portal. So visit Discord and access it there. There's also the data sets that we're going to be using, so you want to upload those. I'll show that in a second. Cool. I'll give you a second to do that in a moment. But Eunice, what's happening in the initializer? Easy one for you.
So you just initialize the super class.
Yep. Which class is that?
The data set.
Yeah, the data set, exactly.
And you just set party attribute prompts to the prompts to the CSV.
Yeah, exactly. So I'm reading the CSV there, selecting the column there. Nice. Brilliant. Alona, can you tell me what's happening in the next two? Sorry, Alona. Yeah, go on.
So we define something.
We define what, sorry?
We define something.
We define what, sorry?
I'm not sure what exactly.
So we're defining a new function. It's called this name. Why's it got that name? What does that do? Faster friend? Magic. What is magic about it?
Yeah, it defines what you call len on that, what's gonna return.
Exactly, yeah. It defines the behavior for when an instance of the class gets put into this function. Like that. So that's what this len method does. When I call this on it, it's going to look at this object, say, hey, do you have a len method? If so, it's going to return it. And then that returns just how many items are in this self.prompts, which is kind of like a list. It's a pandas series, but it's much like a list. Okay, cool. And then who else can help me? David, what's happening in this section here?
Basically defining how the instance should behave when an index is passed in square brackets.
Perfectly worded, exactly. Yeah, defines the behavior for when an instance is indexed with square brackets with an index in between. Fantastic. So index comes in here as the first positional argument, and then it just indexes it. Yeah, that one's too easy for you. All right, cool. So running that, see what happens. We get an error. So this is where you guys need to pay attention. So firstly, go to Discord in the Oxford announcements channel and access this notebook. I've dropped the link there today. So just access that. But there's also a bunch of data sets that we're going to use. The first one is, well, the one that we're using here is the prompt data set. This is the one which is the key one for the reinforcement learning with human feedback step. So get that prompt data set, open up your files here on the left, hit that upload button, and then upload the prompt data set there. Once you've done that, you'll see it in the corner. Close that, and then you can run the cell again, and you should get out a prompt. First prompt, how does gravity work? So take a look at that. Make sure you can do that. I'll just give you 2 or 3 minutes for that.
Are you just performing on a line?
Let me just. Okay, so we've got the data set. That part should be simple. You can see, index it with a bunch of different numbers, check out how long it is and such. Explore that data set. Now, the next thing I want to do is basically take the two models which we got previously, because they're going to be components in the step 3, and I want to show you just two practical things with them. One of them is putting the model on GPU, right? So a lot of you, probably like me, don't have a GPU, and for some reason, I'm not sure how much this is costing them, or if it's meaningful or anything, but Google gives you a free GPU. It's a little one, but it's still a GPU that you can access through Colab. So before I show you how to use that, I just want to get a benchmark of how quickly this thing trains without. So I run that cell just below to pip install transformers. And then in this cell, I've got pretty much just the amalgamation of all our code on supervised fine-tuning. I've got the SFT model. It basically does everything that a GPT-2 language model head model does. It has its own GPT-2 tokenizer. it initializes the model somewhere. Where's the model? Oh, well, it's inherited from the model. So it's got all those methods, like the forward method, etc. anyway. And it defines how to take in a prompt and response, pass them through GPT-2, and get them out the other side. So just stack them together, tokenize them, add the SOS and EOS tokens, and then turn them into input IDs. Get the input IDs, labels, and attention masks, turn them into torch tensors, and then pass them through the model down here. Calls the super method to get the forward method of the GPT-2 class, and then forward to go through that. And then it returns the outputs. So that's the model. And then you've got the data set. The data set here is again, is pretty simple. It loads in this SFT dataset.json. It's just the prompt response pairs that we generated on Tuesday, and loads those in, returns their length, and just returns the prompt response pair for each example. So that's the supervised fine-tuning dataset. And then I've got a new function, train and save the SFT model. It goes through the usual loop and saves the model. So if I run that, just define all those things. And then I'll need to make sure I've got the SFT dataset uploaded as well. So let me just get that. Again, it's in Discord, so download it from there. Any issues, let me know. But SFT dataset.json is now loaded. And I should be able to just run this and start the training. By the way, you guys were not as reliable or high quality data annotators as I had hoped. So I have generated a new data set which is larger and higher quality. So this will this should do a little bit better. And I think, you know, for the time that we get to code today, probably the most interesting thing to do, which is we play around with this. How does it change with different size data sets, different hyperparameters, and what does the loss curve look like, etc. So you can see it training, right? How's it going? 12, 13, 14, 15, okay? So that's the model training currently on a CPU. So what I want to show you is how much faster it is on a GPU. I've already implemented the code, which I'll come back to in a second, which does that. But what I'm going to do now is I'm just going to go runtime, change runtime type, hardware accelerator, GPU. Put it on GPU, save that, run everything above, and then also run this cell. And then let's take a look if it's faster than 14, 15, 16, and so on. So we'll see how quick it is. I'm just going to rerun all of that. I will need to upload my data again. Something going wrong up here. Oh, I need a prompt data set as well. Okay, look at that. Look at that. That's a nice speed up. So it's really flying through those epochs now. So get that running, just run the cells, make sure you can follow that process. Let that train in the background, and I'll explain how to do that. Any issues with the GPU stuff, let me know. Should make sense. Very well. Because it's not seen. Yes. Should make Right, so just to show that again for anybody who missed it, you want to change your runtime type to GPU. So to do that, up here, hit runtime, go down and say change runtime type, and then there's a drop down which lets you accept between GPU, TPU, or CPU?
CPU quicker than GPU.
Is TPU quicker than GPU? I'm not really sure how it works. It's meant to be a anybody know TPU stands for tensor processing unit. Yeah, so it's designed to not just do lots of things in parallel like a GPU is, but to specifically to do like tensor multiplications, those exact operations that we're doing here, specifically for machine learning. That's the initial use case. I don't know how much faster it is, but the point is it should be faster. Try it, figure it out. Print the times between things and see if it works faster for you. But that's that's of key importance there. Like it'll really accelerate things when you have any model which can be parallelized at all. In our case, we have this big transformer. The transformer is highly parallelizable. Can anybody tell me what's the expensive part of doing the forward pass of the transformer? Sorry? I've just re-enabled it. Yeah. So I'm just switching between whilst we're having a conversation at the front here. It should be good now. If it's not working, let me know. The expensive part of the transformer. Do you know, sir? It's all good. Computing the attention. Yeah. Why is it expensive?
So all then squared
Yes, exactly. So we've got a sequence. It's full of T tokens. I like to say T for time, and each of them has a query and a key. Those are the things that basically say. Query says what should I be looking for, and the key says what should I be looked for by. And you want to see how well those things align. So you've got to do their dot product. You've got to do that for every possible pair of queries and keys in the model. And so that's a T by T matrix, like you said, Eunice, perfect. So if you've got a long sequence, that can be very expensive. However, with a GPU, because all those operations are independent, you can parallelize all of them. So even if it's T long, you can do them all in parallel as long as you have enough cores to split them out on. And that makes it usually of constant time, regardless of sequence length, which is really nice. So that's why this is so much faster on a GPU. This will not make your recurrent neural networks faster. You'll be able to split up a batch, but you won't be able to process the different parts of each sequence in parallel. So depending on which model you're working on, this can or cannot be helpful. But in most cases these days with a transformer, it's extremely helpful. So how do you do it? How do you put the model on GPU? Well, let me show you. Let me show you up here. In the model, I've got something else in my initializer, and this is gonna say, just remind myself what I'm gonna say exactly. Yeah. Okay, cool. So basically, you can do torch.device to create a new device. This device is either going to be a CPU or a CUDA GPU. CUDA is the software which runs the GPUs, which used to be horrific to work with. Now it kind of works mostly in the background. But basically, I want to say torch device, either it's going to be CUDA. If you have multiple GPUs, it can be GPU 0, GPU 1, GPU 2, GPU 2, etc. Or it's going to be CPU. So in a handy line that you'll see a lot of the times is one that works in both cases, which is something like this. It'll say CUDA if torch.CUDA.is _ available, else CPU. So this is either going to be equal to the string CPU or CUDA, and that'll basically find out which, this torch.CUDA is available. It'll check, is there a GPU that I can connect to? And then you can create an instance of that device with torch.device. It takes in a string, returns you a reference to like which chip you're talking about. And once you've got that, you can send your model to the GPU, and you also need to send your data to the GPU. They need to be on the same device to compute together. And the way you do that is by, if you've got an instance of a model, you do model.to and pass in a device. If you've got data, you do that tensor.to and to the device. In this case, I'm inside a model. So what could I do here? Everybody see where I'm going with that? Yeah, that's not obvious. I could do self.to, okay? Because this is a model. So I could do self.to and I could pass in the GPU there, basically. I had another line here before I deleted it. So what was on that? Let me not forget anything. Yeah, that line is not important. There's another thing you can do. You can do self.device. That'll tell you which device the object is on. I think that's a method. Anyway, but that's the important thing there. Basically, that's me moving this model to my GPU. So if you have a model you want to accelerate, you've got a GPU, that's what you need to do. Outside of the model, you could do something. Well, outside the model, you could do something like this. Equal to SFT model, whatever it was called. Then you could do model.to. And then you pass in your device there. And what I did was, because I was already inside the class, and self always represents this instance of the class, I just did self.to, because in that case, self was an instance of model, because it inherits from this. So I moved it to the GPU, and then in the forward pass, I also got to do the same for the data. It's very simple. You simply do the tensor, which I've got so far, .to, and then pass it into pass in the device. So in this case, self.device, like I said, represents the device which this model is on. But otherwise, it could be, you could have something similar in there. GPU if torch.cuda is available, else CPU. So that's how you move something onto GPU, which can really accelerate it. Anybody want to ask any questions about that?
Is this pretty standard? You see this in the code?
Yeah, very much. Yeah, very much. I'm not sure of the most efficient ways where to put things in, because I don't know about it, but there's like some overhead between moving devices, of course. So you don't want to be doing that like all the time. If you have big enough GPUs, ideally you can put all your data on the GPU just once at the start and then run like many epochs, and it doesn't have to be moved around. What you don't want to be doing is moving huge data sets between the devices, because I think that's pretty expensive. There's probably some computer scientists here who can tell you more about that or help me out with it. But this is at least doing it, and you can see in practice it's pretty quick.
Why the argument rules are the same?
Great question. Eunice's question as well. Just to recap here, we've got we're doing the forward method of the GPT-2 LM head model, takes in input IDs as input IDs, and takes in the labels which are equal to the input IDs. Here's where it is. Why is that? Well, it's because if you look up Hugging Face, GPT-2, go to the documentation. That's not the documentation, that's the model card. I want this one. Then scroll down to the LM head model, which is what we're using. We'll look at the forward method of that model. In the parameters, you can see what it expects as the labels. Always best to look at the documentation rather than assume what's expected by different things or different libraries that you're working with. But in this case, the forward method takes in the labels, and it says here, note that the labels are shifted inside the model, i.e. you can set labels equal to input IDs. So the most common use case for this language modeling head is like predict the next token in the sequence. So to make it easy, nice and user-friendly, which is what Hugging Face is known for, you just pass in two of the same thing. And inside the model, it will take the one you set as labels and shift it along. You can also pass in something totally different if you're doing like translation or something like that. But this just makes it easy to predict the next word. There's probably a parameter to toggle that as well. Yeah, great question, G. And yes. This is optional, correct? Yeah. What happens if you don't pass it in? I wonder. I don't know. Will it give me an error? Yeah, I think it's only needed in the training, because when you're doing inference, obviously you only want to, you don't have any labels. Comment it out, try it, see if it gives you an error. Otherwise, maybe it does just accept by default. Although I think, yeah, probably doesn't. Okay, cool. So that's an overview of the model and how you put it on GPU and everything. Everybody comfortable with that? SFT model, very nice. so the next thing that I want to mention, again, just second practical trick for you here, is something I haven't really talked about yet, but that's saving the model. So to save the model, I would do this. I do torch.save, and I could just save like self, right? Or I could, if I was outside the model, I could say torch.save the model, and that's going to take everything inside that variable. I think it's going to pickle it, which turns it into a serializable format, and then it's going to save it in some binary file or something along those lines. However, this is probably this is not the recommended way to do it, because this saves both the model parameters and the model architecture in the same file. And if you want to change the model architecture later, I think the problem is that then it can be then you have to basically give up the weights as well. So what you want to do is is keep the class saved separately, probably in GitHub, and just save the model parameters, tag them, make sure you know which class they belong to, and then load them back in. So that's what we'll do in a second. So in this torch.save, I'm not just going to save self. I'm going to save what's called state dict. So the state dictionary is the state of the model. It's all of the different layers containing all the different parameters in a dictionary. So it'll just say, say like linear layer 1 has these parameters, transformer, decoder, weights in head 3 have these parameters, etc. And it'll store them in just a big dictionary, basically. We could actually look at that in a second. And then the only other thing it wants is a file name, typically with a PT extension, .pt for .pytorch files, so PyTorch weights. So I'm going to put that back there. And did mine run completely? Not sure. Yeah, so I've saved their SFT model params. I don't want to download them because there's 1.5 billion of them. And my computer gave me a memory error yesterday. But those are the parameters. Feel free to look into those if you want. They're in some binary format. But when you load them in, which you can do just like this. So the opposite of save would be load. Give it a file name. And then that's your state dict, basically. Let's take a look at that very quickly, because that's actually a good example of what the state dictionary is. So here's the state dictionary. It's massive. It's a massive dictionary. I can't even scroll all the way to the top, but you can see it seems to be like a list of tuples or something. And this one, it says, okay, this one's transformer, head 11. These are the multi-layer perceptron projection from, not sure what C proj is, but the projection somewhere. These are the bias of that layer. So you can see even in the bias of that head, of that layer, of this part of the transformer, there's like a load of parameters. So this thing has all of that stuff inside. Here's the fully connected weights, etc. So feel free to take a look at that. But that's what's in the state dictionary, and that's how you load and save things in. Save the state dictionary, keep your class, keep it in GitHub, make sure you know which model you saved it for, and then you can load them back in. Once you've loaded it, or once you've saved it, you can load it in just as I said there. And if you run that, this is the new line. It says, I've got a model, and you can do .load state dictionary. Load state dictionary looks at that dictionary and makes sure it matches up with the model architecture, and then puts the right parameters in the right place. When it does that, it says all keys match successfully. And that means that you've loaded in those weights into your model. So here, that's it. We've trained the model, saved it, loaded it in. The SFT model is ready and ready to use. The next thing is the pre-trained reward model, which is basically the same. This is what we looked at yesterday. Just to recap quickly, it's got a different loss function, which takes the difference in reward between the two different responses which you give it. One of them is preferred, one of them is alternate. It normalizes those between 0 and 1. It takes their log, and you want to minimize their negative log mean over a batch. And then in the data set, we're basically returning pairs of preferred and alternate responses to a single prompt. So the model here is going to take in a prompt and a response and predict how good it is, what's the score, we want the score for this response to be better than this one. That's what we're training the model to do. Give that higher score. It should encode those human preferences. And then finally, in this cell, I think I've got the next thing in the cell, I've got the reward model, doing a similar thing here, setting the device, sending it to the device, the forward method, in this case, passes it through GPT, but then it also passes it through a regression head, calculates a single number, that's the score at the end of the day. And then train and save that in exactly the same way. So I'll run that quickly. Train and save it. And then I'll wait till that's done to load it in. So run that now. Take a look over those, the GPU and the save stuff, because that's important. And I'll wander around. Make sure you got that reward data set uploaded as well. Fantastic. Yeah, the two methods probably are. No, that's not what. All I'm saying is that I think that that's like makes up directly all the time. Okay, yeah, so I just hit an error which someone may be aware of, which is this is not the name which I saved the params as. So I want to take that and replace it in here. So if I run that, I should be able to load in the reward model. Okay, so now we've got those two things. Those are the two components of this RLHF. So the next step is to define this objective, the thing which we want to maximize now, thing which basically indicates, okay, this is good behavior for the model. So I've got here, it's a pretty simple function. It says the reward maximization objective. It's actually pretty trivial. All it does is puts the reward model in eval mode, evaluation mode. That's changes the behavior for some things, for some different layers inside the model, which you don't want to happen when you're putting it into production. And then it just calls that model on the prompt and response, gets back a reward. So that's the score, which is computed from the supervised fine-tuned model after it goes through the reward model. So this thing depends not only on, it depends on the response, which comes from the other model. So what we hope to be able to do is to pass the gradients all the way through this reward model and and calculate the gradients in the supervised fine-tuned model and only update the SFT model. So this is the function which defines the maximization objective. Run that, and then here I've got another final function, and I'll talk through. I'll give an overview of this right now. So in here, looks much like we've seen before. I'm creating the summary writer for my logging, creating the prompt data set now. So it's just going to be a list of different prompts. Create the reward model and the SFT model, because they're both needed for doing this RLHF. Then I create the optimizer, iterate through the data set a bunch of times, and go through all the prompts in each epoch. When I get each prompt, I'm going to use the SFT model to get the response. And then I'm going to get the value of the objective. The objective comes from that reward maximization objective. And then I do this. Why do I do this? Why do I do this line here?
Because it's going to minimize the loss.
Continue. Why is it negative? I've not done that before. Ishwa?
Because when you're doing lost up backward, etc., you want to move across the thing where it goes decreases, right?
Mm-hmm.
But as we have it currently, this is going to do exactly what it's going to make the objective lower. So you want to flip the sign.
Yes, exactly. So by default, when you do optimizer.step, the optimization algorithm they say move downhill, basically. But in our case, the objective is not something we want to minimize. Exactly. It's something we want to maximize. So the way to maximize something is just minimize its negative. So we just flip upside down. Uphill will be downhill, and it will go the opposite direction. Exactly. Great stuff, Shwa. So flip that upside down, and then we should be able to do objective.backward. Objective.backward is going to populate all of the gradients, and then we just got to do update those gradients with optimizer.step. Finally, zero the gradients, and then add scalar at the end, and just do the logging. And then finally, I'm saving that model. So let's just kind of zoom back in on a few things. One of them is the optimizer here, right? Importantly, it's only optimizing the SFT model parameters. It's not optimizing the reward model's parameters, because we want the reward model to stay fixed, because it's been fit to those human preferences based on the ranking data set. So we only want to optimize that one. Now, we still need the gradients to be calculated inside the reward model, and they will be when we do .backward, because the things that I'm trying to optimize are, they go through that reward model, but we're not actually going to use those .grads. So that's roughly what the function looks like. However, I have to make a big disclaimer, which is something that I only realized too late to fix, and I'm not quite sure exactly what the implementation should look like yet, so I'll update you on it. But there's a problem with this. Has anybody realized the problem? Why is this not going to make the SFT model any better as I run this? Tough question.
I don't know if the gradient will flow into the SFT and update parameter reset method.
Why is that?
Does the PT SFT model parameters that file, like within that file, each one have like grad true?
Yeah, do they have requires grad true? Well, that would certainly be one thing to check. Yes, I think they do. They do to start with. If they don't, I can I could iterate through the model and do that, or maybe I can do something like model.train. I don't know if that does it actually, but I could change them. Yeah.
Maybe the parameter that file doesn't contain the structure of the model.
Well, the parameters don't contain the structure, but we've loaded them into the class, right? So we've got everything. It should be in the right place. Yeah. Alex?
Does setting the reward model to eval mode stop it from propagating gradients backwards?
Does setting the reward model to eval mode stop it from propagating the gradients backwards? No, it doesn't. It just changed the behaviors of the layers. So there's really a mathematical problem here. Answer? It should be fine as long as. So tell me what you're thinking.
Is like you define the objective using the reward maximization, but then you're calculating backwards on that, but then you don't necessarily have the SFT model.
Yeah, so it might look confusing here. Like, okay, well, we're not using the SFT model to compute things. It doesn't appear in this objective. So is it being optimized? Now my thoughts were, so that might not be obvious, but actually we are, because this response, that's the output from the SFT model. So if we go back to the diagram all the way above, which shows this here, this reward is really a function of the response. And what we're trying to do is we're trying to do objective.backward so that it fills up all the gradients in here, gets to this tensor here, which is the inputs, the inputs, the reward model are the outputs of the fine-tune model, and then continues backward through the output there. Now the problem is that these inputs, they're input IDs. Those input IDs could be tensors, but I think there might be a list in our case. If something isn't a tensor, then it doesn't have a grad function. So it doesn't know how to calculate the gradients before. So I think that'll be an annoying problem which we could solve, like just change the outputs of the SFT model so they stay as a tensor, change the inputs so that they accept a tensor instead of a string. Right now, both these models input and output strings. But the problem is actually even worse, because inside the last layer of this supervised fine-tuned model, well, it's got predictions. How do I turn those probability distributions for each word into the actual word? I take the argmax. What's the problem with that?
You lose all the it's not differentiable.
It's not differentiable. Yeah, the argmax is not differentiable. So the argmax is not differentiable. What do I mean by that? Well, the argmax is saying basically tell me the position of the biggest element in the vector. Well, what does it mean to be differentiable? It means you need to have like this nice smooth function, and you can see how steeply it's going to change at any point. If I have a list of 3 numbers and one of them is much bigger than the others, no matter how I change them by a little bit, it's always going to be the biggest. So the gradient is 0 until one of the other numbers suddenly just gets bigger than it, in which case the gradient just changed massively at that point. So it's not a continuous function. It's not differentiable everywhere. And because of that, we can't backpropagate through it. So that's the problem with this implementation. Ishwar?
Yeah, so to fix that, you can just take the top part of the probability of each word and then reward each word.
Could you take the, sorry, say that again?
So now you have like probability distribution for each word.
Yeah.
And you can calculate the reward for any word. Could you just calculate the reward for all the words and then dot that with the probability?
So you can't calculate the reward per word. The reward is for the whole sequence, because the output of this reward transformer is a bunch of vectors. We take the last one, should contain all the contextual information from the others, but it contains all that information. So it's like you can't just reward per word, otherwise it might just say nice words in a sequence without making any sense. Yeah. Good attempt though. Yeah. So I'm actually not sure of what the right implementation is here. So I'm going to go away and fix this. So even if this doesn't let us actually run this thing, it should, I hope, give an idea of like how these things are laid out. And I think that's probably the more useful thing, to understand how the system works rather than actually be able to implement it yourself. I'd love to work with a few people and try and figure out the right implementation for this over the next few weeks or something. But right now, this isn't going to work. Yes.
Could you just take a argmax bit so that your response is a vector and that goes in as a vector?
Yeah, so could you take out the argmax? So if we didn't have the argmax, we'd have an output of probability distributions. We'd have T by embedding size probability distributions. The problem there is that can't go into GPT-2, which is the reward model, because GPT-2 expects indexes, which it can then embed in its first embedding layer. So I thought I looked something down when I was thinking about that, but yeah, I don't know. I don't think you can take it further there.
Can you do something?
Sorry?
Just something over that distribution.
Could you sample over the distribution?
Yeah, I don't know if that's something process is different.
It's not differentiable. Yeah, it's not differentiable. I don't know. I'll buy someone a hoodie if they figure it out, but otherwise I'm gonna be on it and try and crack that. So that's roughly like what's happening, right? You want to predict a reward using the response and the prompt, where the response comes from the SFT model, and then you want to maximize that reward. But unfortunately, this isn't going to work. So I want to talk through, I want to get a little bit closer to what was implemented in the paper and explain this as a final last interesting thing. So this is the overall objective, or it's most of the objective they used in the Instruct GPT papers, which explain this process of reinforcement learning with human feedback. So firstly, let me just show you the paper, and maybe I've tagged this somewhere in there, maybe not, I'll share it later. But in there, you can find the full details of this. And at some point, you come to this objective, which it looks really horrific when you see it, as a lot of equations do. But most of the time, you can break them down into something which actually makes a bit of intuitive sense. But I want to focus here because this is the objective, which is like the main thing that's being used to tune these large language models to align with human behavior. It's optimizing this objective. So this objective, yeah, it looks horrific. There's like the reward term there. You've got this log of 2 different policies, and then you've got this other term on the end here. So what is that? Well, I think it's better explained like this. So in color, in full color, you can see that the objective to be maximized is the expected reward sampled from your data set, which we're using for this reinforcement learning process. Penalized, so that's the reward there, but it's penalized by the scale difference between the new language model and the original fine-tuned language model there. So basically what this is this extra term makes the new model stay close to the one that came out of the supervised fine-tuning model. It can still move away, but it's gonna get penalized for that. So the reason you want to do that is because if your objective is just to maximize the reward, well then you can just learn a different distribution which the reward model gives you high scores for because it's never seen before, and it will just be gibberish. That's the kind of thing that I think you see when you don't have an objective function like this. You'll just kind of game the reward, essentially. You give it a prompt, which is just a random sequence of punctuation, and the reward model's never seen anything like that. So it's usually looked at things which are over here. It suddenly receives a response which is from over here, and what's it going to do with that? You don't know, because it's not been conditioned to predict the correct responses for that sort of thing. So if you're able to just output whatever text, there's probably some arrangement of the text which you can trick the reward model with, get a high score for. So this term is meant to minimize that.
Where is the human feedback?
The human feedback's in the data set.
Which one, the one we used yesterday?
The ranking data set, yeah.
It's like the most first paper and paper. That's
Yeah, exactly. That the ranking of the tasks, that's the feedback there. Yeah.
so, but But you use the like reinforcement learning with human feedback in step 3. Actually, the
Yeah, so
feedback is in step 2.
it's like both. Yeah, so this is the reinforcement learning part of it, but to do the RL, you need that model which encodes the human feedback on prompts previously. Yeah,
In reward.
yeah, exactly. Yeah, that was my understanding of it, at least. Yeah. So yeah, if you're interested, this is like the KL divergence between the two distributions. So it's just a distance metric between probability distributions, really. This is a probability distribution. It's a probability of the next word, y, given, it's probability of the response, the whole sequence, given the input. And this is the probability distribution, the language model, which we initially did the supervised fine tuning on.
So can we interpret this as like a regulation parameter?
Yes.
The parameter change to.
Yes, exactly. Yeah. You can interpret this as a regularization term, because if you can fit very well to the rewards which have been ranked, that's great, because it's going to do well on those examples again. But then it's going to do nothing well for brand new prompts. And so in those cases, it might just put out gibberish. So this is a good example, of a regularization term which makes it stay close to what we know is a good language model. It's been trained well to do the supervised fine tuning. So understanding that, like, that's the main objective for how these language models are learned. So I won't talk any more about it, but I'll leave that to absorb in there. So now I'd like you guys to at least spend 10-15 minutes, play around with the language models, see what results you can get. Look at TensorBoard as well. So we've trained a bunch of stuff up here, and if you want to see what that looks like, just remember to add this line. Load ext TensorBoard percentage TensorBoard -- logdir runs, and all your runs are stored in here. So run that cell, and then you should be able to see what's happening. Is it working? Let me know. How well is it working with the new data set? Have a play around with it. It didn't work for me, so have a go there, and I'll try again. But yeah, take 10 minutes to do that, and then I'm gonna do a quiz. Yes. And this is your last chance to post a picture of these lectures with a nice diagram at the front. So if you're going to do it now and you want to enter, now's your chance. And I'm going to take a moment to look through all of that. It's the last day. Post how much you learned. Post how epic it's been. Post what you're going to do with this stuff. Post the results. Post the graphs. Post this thing looking cool. Take a screenshot. But let the world know that you're in this top minute percentile of people who actually understand anything that's relating to the big hype that is ChatGPT right now. Okay, cool. So there's only 15 minutes left of this final lecture. That's all the technical content I want to go through. What I want to do is a final thing, and then to give out some awards, is to do this quiz. So I'm going to pull this up. You guys can check it out on your phones. I'm going to do a challenging quiz on topics of ChatGPT and transformers. The winner gets a prize. The winner gets £100. And they also get a hoodie. And the runner-up gets a t-shirt. So, you better be excited for this. And then I'm going to look at all the LinkedIn posts later, and there'll be a prize for that as well. So, get yourself online here. Try and use your own name so I can get an idea who's who. It's meant to have music too, but I can barely hear it at all. Okay, and then after this, we're going out to get some food and to get a drink. And then after that, we're going to have to do something even crazier. So, this is your chance. This is your chance to win cash prize and a hoodie or a t-shirt if you're second place. Equally valuable. So, jump in, we're going to get started. Are you ready? I've given away a lot of the answers throughout this session, by the way. So if you're paying attention, you're an advantage. This is the Transformers and ChatGPT summary quiz. Are you ready? Woo! Let's go. Language modeling means. What does it mean? We've got 20 seconds. And time counts points as well. Don't stress, this is one of the harder ones. What's happened here? There we go. Nice, 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 cool. 15 correct. Language modeling means modeling conditional probability of a next token given the previous one. Not specifically for human language. Can be used for all other kind of things as well, like code. Doesn't have to be for conversational behavior either. Translations, anything like that. And doesn't necessarily mean that you need to be able to perform highly on the tasks. All right, who's up there? Josh? Go. Okay, Ray closely following. Nice, nice. Let's keep it going. All right, puzzle 2, 12. In what order do the following steps take place in the training of ChatGPT? You better get this one. Come on. You've been practicing for weeks. You better get it. Time matters, so get your answer in quick. Yeah, warning, there is a fourth step here, which I haven't highlighted, so make sure that goes in the right place. All right, there we go. That's the right order. Data collection, supervised fine-tuning, training a reward model, reinforcement learning. Woo, Josh still up there. Jay? Who's Jay? Who's Jay? Getting close, like it. Okay, cool. Let's keep going. Ray, still there. G, up on the spot. Eunice, coming for it too. All right, this one you got to type. What's the dimensionality of Bert's word embeddings? Flying in. That's it. Five, four, three, two, one. Dimensionality is 768 dimensional. 15 of you right. Nice, on the money. Oh, it's shifted, man. Jock, I seen the look in your face. DF, who's this? Who's this? Yes. Okay, cool. Jinghua, all right, we're up there. G, you're on the street. That means you get extra points next one. It's the same as how many layers it is. It's 12. That's right. 12 heads in GPT-2. Okay. How things shifted? Oh, Josh, you're off, man. I thought you had it. I thought you were strong at the start. Okay. DF's got it still. All right. Jinghua, G, back up there. All right. Ishwa, come on. Get a streak now, and then you can overtake them. Intention, the keys can be thought of as what should I be looked for by is what the keys tell you. Scoreboard. Oh, it's shifting all over the place. Richard, out of nowhere. Where's Richard? Richard, got it, cool. All right, G, still up there. Ishwa, nice, zooming in. Eunice, you can catch these guys. All right, we're halfway through. For a batch of B inputs, length T, into a transformer with H heads and hidden dimensionality of D, attention size is... Come on, there's just an easy thing you need to recognize here. There's the golden rule, and there's the what's the expensive part? Nice. That's it. Yeah, that's the one. Okay. What's the golden rule? First dimension is always the batch dimension. And what's the other part? What's the T by T? Sequence length by sequence length. That's the expensive part to compute. Fantastic. Cool. Good stuff. A lot of people went 6, B by B. That was a trick. There's no double duplication of the batches. They don't interact in any ways. First dimension, batch dimension. Where are we at? Oh, G, yes. Eunice, okay. Coming in. Ishwa, keep it up. Okay. Richard, come on. You can catch these guys. All right. What would be the output dimensionality of a sequence? A day well spent if it were passed through but, so tokenized and then passed through but. See a lot of calculations going on here. That's right, the dimensionality, contrary to popular opinion, is 6 by 768. Why is it 6? Why is it not 4? The CLS and the SEP, exactly, yeah. It's got a start of sequence token and an end of sequence token. G, you're up there. Ishwa, come on. All right, type your answer. In PyTorch, all classes except for sequential layers and the RNNs, the batch dimension is found in the what dimension? Yeah, I'm gonna get this one at 10. You already got the answer. It's the first dimension. Only 8. Come on. What's going on? Okay. All right. Things shifting. Stakes are high. All right, puzzle. Keep it up. Keep it going. In what order the following things happen to the input of the first decoder of an encoder-decoder transformer? What happens? In what order?
Can you see the diagram in the t-shirt?
Yeah, Peyton, stand up and show us. Peyton got the t-shirt on. This one, I don't know why you got so long for it. In the first decoder. Yeah, I'm going to skip it when we got 25 answers. All right, that's the order. Firstly, positional encoding. This is the first layer. Then masked multi-head self-attention. Multi-head cross-attention, because it's an encoder-decoder transformer. And then followed by a single feed-forward layer neural network. Of course, you've got add and layer norm there and there. But I couldn't put that in 3 times. Okay, how's it looking? How's it looking? Ishwa's up there. Jinghua, T. Slider. Okay. Instruct GPT can generate preferred responses compared to GPT-3 despite having how many times less parameters? Is it 10 times smaller? Is it 200 times smaller? Somewhere in between, maybe. I'm not sure what the trade-off for accuracy and speed is here. I'll give it. Oh. Oh. It's 134 times smaller. 0 people in the range, but it's 1.3 billion versus 175 billion. Scoreboard. Raise the highest climber. Ishwar's still on top though. Ishwar is coming in good. Okay, two more shots. Which dataset used in RLHF requires both the prompts and the responses? Okay, 25 in. It's the SFT datasets. SFT dataset, you need to know what are they. Well, you need to know the whole sequence. You want to model all of that kind of language data. So you need both. It's not the reinforcement learning. It's not the dataset, and it's not the reward dataset. That one requires the rankings. Scoreboard. Ishwar, oh, it's looking good. Come on, someone get him. Double points this one. Training the reward model requires what? The whole point of the reward model was that we don't need a label, right? No, it was a trick. And that's the final. It's the prompts and responses, the inputs, the label, as the rankings. Can I get a... Podium, what's going on? 3rd place, Eunice. Well done. 2nd place, G. Well done. 1st place, the big prize. Ishwar. Well done. You've been diligent and loyal. You've been here almost all the times. I really appreciate it. You deserve it. That's where your knowledge comes from. Fantastic. So, guys, that's it. I'm going to wrap up here. This is the end of the ChatGPT lectures. That's 10 sessions. Hopefully it was useful from neural networks to ChatGPT. Any questions, you can hit us up on Discord. And hopefully, yeah, this will put you in a really good position to be a part of all the exciting stuff that's happening with it right now. I've put in a lot of effort to deliver this. It's been my pleasure, of course, but I hope if any of you want to come and do any training in the future, if you are at your company and you can get them to pay for your training, you should come and learn about more of the state-of-the-art stuff. I hope AiCore will be your first choice. If you aren't already in a career, don't have anything lined up, let me know. We can help with that as well. And if your friends are in any of those situations, let us know. Hopefully, we'll be back soon, but thank you so much. Okay, right, you're gonna do it. G. Big one. Well done, sir. Well done, sir. Get this. Right now. Oh, wow.